Hello, I'm Grace, and I will be talking about electron beam instabilities and helium-3 acceleration in solar energetic particle events. Okay, so starting off with some background, solar energetic particle events are events in which the sun produces this electromagnetic radiation, which has effects on the Earth, such as geomagnetic storms that can cause blackouts, and actually relevant to this weekend, apparently, there's going to be auroras visible throughout the states, which is caused by solar flares. So in solar flares, recent observational data from the past few decades has shown this overabundance of helium-3, which is over what is expected by up to a factor of 10 to the fourth. Helium-3 has a unique charge to mass ratio of 2/3, as opposed to helium-4, which has a charge to mass ratio of 1/2. And because of helium-3's unique charge to mass ratio, it is thought to be accelerated during magnetic reconnection by plasma wave cyclotron resonance heating. And the source of the waves that's driving this acceleration remains an open question. So that leads into the question that I was exploring: what drives these waves? Data from very recently, the Parker Solar Probe's exploration of the solar corona, alongside simulations done by others, have indicated that ion beams are a likely driving mechanism. But another source that has been posited is that electron beams could be wave drivers, and that is what I looked at. So the model that I focused on is an electron two-stream instability, which is just you have a stationary population of ions and then electrons at equal drift velocity, one positive, one negative, and the electrons are equal density. This is by Maxwellian distribution. And the program that I used to actually produce results is called Arbitrary Linear Plasma Solver, also known as ALPS. And what I did is I just inputted values that are relevant to the solar corona. So this is the parallel wave number. This is the Alfvéan speed over the speed of light. And these two, I'd like to note, they apply to all three of the species populations, so both electrons populations and the ions. And this is just the perpendicular temperature over the parallel temperature, and this is beta, which is a constant that is related to the temperature. So I used ALPS to find linearly unstable modes, which occurs when the imaginary frequency is positive, because if the imaginary frequency is not positive, then we have damping, or basically damping is just not what we want. That's the opposite, because it won't accelerate the particles. So the resulting map that I got from ALPS this is a plot of the imaginary frequency versus the real frequency. And up here you can see a mode. The dark spots indicate the modes. Down here, it's harder to see because it's zoomed out a little, but there is a mode there, I promise. So there's two modes that we found, one of high frequency and a second mode at a lower frequency. The second mode is what we care about because this is close to the ion plasma cyclotron frequency. And we had to compare the results produced by ALPS to theory. So this is an equation for the dispersion relation. And we assumed this limit, and then using a Taylor approximation, we found that the theoretical value for gamma, which is the imaginary frequency or the growth rate, is equal to 775. So the lower frequency mode is reasonably close to the theoretical value for the ion plasma cyclotron frequency. And so in conclusion, the existence of an unstable mode at a value reasonably close to the resonant ion plasma cyclotron frequency suggests a possibility of the electron beams as wave drivers, and future work can explore more sophisticated distribution functions to confirm the possibility, because the distribution that I looked at was rather simple. So thank you. Questions?